So I'm defining the ports that are required for RCA. One is Q is my output, and clock, comma, reset. Clock and reset are my inputs. So I'm defining output, which is a 4-bit output. So 3 down to 0, semicolon, and then input, which are clock, comma, reset. They both are single bit input, so I am not defining the width here. Since see the red mark showing there is an error, the error is spelling mistake. Since the ripple carry adder requires 4 T flip flops, I am calling 4 T flip flops like this. TFF is my T flip flop. Right now I don't have the definition of T flip flop, but I will define the T flip flop in the next module. So T flip flop, I'm calling with name TF1, and I am assigning Q of 0, comma, clock, comma, reset to the first T flip flop. And TF2, I am assigning Q of 0, no, Q of 1, comma, the clock for next flip flop will be output of first flip flop, right? Q of 0, comma, reset. Similarly, TF3 and TF4 will copy this, paste them. TF3, comma, TF4, this will be Q2, and this will be Q1. Similarly, this will be Q3, and this will be Q2, right? Now, this is a ripple carry adder, but we don't know what is the definition of T flip flop. So let's define what is a T flip flop. I'm creating a module TFF, the same name I'm using here, module TFF. In module T flip flop, I have inputs like Q, comma, clock, comma, reset. And end module. Now I will write my output Q. Since it is a 1-bit output, I am not defining the width, and my inputs are clock, comma, reset. Inside this module, what do we have? We have a D flip flop and inverter. So I am defining a wire D, and I am defining a D flip flop. Right now I don't have definition of D flip flop, but I will define it in the next module. D flip flop DF1, and the inputs are Q, comma, D, comma, clock, comma, reset. So I need an inverter, so I am directly using the NOT, which is a primitive that is available in Verilog. NOT N1 D, comma, Q. So Q will be negation of D. I mean D will be negation of Q here. And module. This is T flip flop. Now I want to define what is a D flip flop is. Module DFF. My inputs are Q, comma, D, comma, clock, comma, reset. My output is Q, and my inputs are D, comma, clock, comma, reset. I required a register of Q. Now I am using an always statement. I will define what is always when I explain you behavioral coding. Right now I am using an always statement, always at the rate passage of clock or reset or negate of clock. I'm using negative edge flip-flop, so I'm writing negate of clock. What I want to perform, if my reset is equals to 1, then my Q will be set to 1 tick binary 0. Else my Q will be set to T. I am ending the module of D flip-flop. There is an error, clock, syntax error near clock. Why this error is coming? Negate spelling is wrong. Now there is no error. See, in the same file, I have defined 3 different modules. You can define any number of modules in a given file. Right now, we have designed the ripple carry adder using T flip-flops, which are designed by using D flip-flop and an inverter. So for this, we'll create a test bench also. So how to create a test bench? First of all, save this design source and then create a simulation source. So I'm creating a test bench, which I will call top module of RCA, top of RCA. I don't have any input output force for top module, so I will directly write the stimuli code. Until and unless you call this RCA inside this top, the first module will always be at the top hierarchy. So I am calling this top. You can even see how the RCA is built. The RCA is built using 4 T flip-flops, TF1, TF2, TF3, and each T flip-flop is built using D flip-flop. This is what the hierarchy I am talking about. You can see the top-down approach, right? The RCA is built using T flip-flops and the T flip-flop is built using D flip-flops. And now if you call the RCA inside the top module, you will get the top as the top module and RCA is called inside the top module. We'll see in a few minutes. Module, I required a register of clock, comma reset, and then I require a wire of output 3 down to 0 of Q. Now I will call my ripple carry adder. The name is RCA. My ripple carry adder module name is RCA, right? So I'm calling with same name RCA with R1. I'm assigning in the same order, but I will prefer connect by nets. So first of all, I have to connect this Q, clock and reset with my own Q, clock and reset. How to do that? Dot Q with this Q, dot clock with this clock, dot reset with this reset. Now the port mapping is done and RCA has been called. Now we'll give the test vectors. Test vectors. So let's apply some test vectors using initial statement. Initial, begin. I want to give a clock with a time period of 5 nanoseconds. So initially clock is equals to 1 tick binary 0 and then initially the clock is 1 tick binary 0 and I want this clock to always toggle at 5 nanoseconds. So the syntax is like this: always after 5 nanoseconds I want the clock to toggle. So how to toggle? You just use the unary operator of not. Clock is equal to clock bar. So after every 5 nanoseconds the clock will be toggled. This will create a clock of 10 nanoseconds with on time period of 5 nanoseconds. Okay. Now I want to give, this is creation of clock signal. Now let's apply some input patterns. Applying input patterns. So here I will start with initial, begin, reset. See, always I have used only single statement, so I haven't written begin and end, but it is always a good practice to write begin and end. Begin and end. Similarly, here also initial, begin. I want initially the reset to be 1 tick binary 1, and then after 50 nanoseconds, I want reset to be 1 tick binary 0, and again after, let's say, 120 nanoseconds, my reset will be 1 tick binary 1. Here the only input is reset. I am controlling the ripple carry adder by using an asynchronous input called reset. Let's end this and let's monitor the inputs by using again initial. You can write any number of initial and always blocks inside a module. Initial, I'm monitoring the inputs and outputs. Monitor at this time period time, my output Q is equal to %d. I want to see in the decimal format, comma Q. The 4-bit Q value will be printed in decimal number. Let's end this module. There is an error here. Rec. I have to write reg, but I have written rec. So reg. See, whenever there is a Verilog data type appears, it changes the color. So I'm saving this. Once I save this, the top will become the top module. Now there is a syntax error somewhere. It is showing red. So it is at here. See, I haven't closed the semicolon. Now save it again. No errors. It is in green color, and you can see the top is calling the RCA, and the RCA is calling the T flip-flops, and each T flip-flop is calling its own D flip-flop. So let's run the simulation and see the output. So let's see the output. Yes. See, it starts counting 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, A, B, C, D. And then since there is no time, after some time we have set reset to 1, it start resetted. So let's use some more time to get all the values. So let's define this time as 50 nanoseconds and run the simulation again. You can see the outputs here also. See, at Q time is equals to 0, Q is 0. After 50 nanoseconds it is 1. Then after, why? Because after 50 nanoseconds, because we have applied reset is equals to 0 after 50 nanoseconds, right? And from this, after every 10 nanoseconds, because my clock time period is 10 nanoseconds, after every 10 nanoseconds, my count starts incrementing 60, 70, 90, 80 like this up to 15. Since it is a 4-bit counter, it starts from 0 to 15. The same thing you can see from here. Until the reset becomes 0, the output is 0. When the reset becomes 0, then it starts counting these clock edges. This is the first edge. This is the second edge. Since it is a negative edge flip-flop, it is triggering at negative edges. This is the first edge it encountered, second edge, third edge. If you want to see the queue in terms of binary, you just right click, radix and binary. You can see the binary values. And if you want to see in terms of decimal, unsigned decimal, you can see the decimal values. 15 after 15. After that, I have set my reset to 1, so my counter output becomes 0. Since I haven't set my reset to 0 again, for all the time it becomes 0 only. So this is the functionality of a ripple carry adder. Now let's see its schematic, and then we will do the synthesis by using constraint file, and we will implement the design in a Zed board. So let's start seeing the RTL schematic. So here you click RTL analysis, open elaborated design and click on schematic. Okay. Now you can see the schematic of your ripple carry adder. It is elaborating the design. See, this is your ripple carry adder. It has 4 T flip-flops, TF1, TF2, TF3, TF4 and one output pin. The output direction is like this, and 2 input pins. The direction are like this, clock and reset. And the T flip-flops are connected like this. The first output is connected to second input, second output, third output like this. So this is your T flip-flop. If you double click on this, you can see the T flip-flop and inverter that the T flip-flop is made up of. The T flip-flop is made up of by using a D flip-flop and an inverter, right? The Q is passed through D by using an inverter. And the clock and reset are directly connected. So you can do back. So it is showing total 3 cells are used and 4 nets are used in this, right? So this is how you can see you can visualize your schematic. And next step is to do the synthesis. So I'm running the synthesis with all the cores I have available, and okay. The synthesis is still running. You can see running synthesis design. So it will take some time. Meanwhile, we need to create a source called constraint file in order to implement the design on Zed board. So I'm creating a source, add a constraint source. Let's see the synthesized design first. The synthesis is complete. So I'm opening the synthesized design. I can see the schematic of the synthesized design. So this is the synthesized design. So you can even report the power, report the utilization, everything, how much power it is consuming, how much resources it is taking. We'll explain all these things in the advanced topics. But right now, I want to concentrate on implementing this design on Zed board. So I have to create a constraint file. I'm adding a constraint file. Next. So I'm adding the constraint file. Before adding the constraint file, I need to download the constraint file from Google. You just search the Zed board XDC file, then you will get a GitHub code of it. So this is the XDC master file that was provided by the Xilinx company itself. So copy this entire text and paste in a new text document like this, and save it with an extension of .xdc, zedboard.xdc. So once the XDC file is created, you just copy that file here and then finish. Now see the master file. From this master file, you need to edit few lines. In your design, you have one input which is reset, and clock is also an input, and Q is the output. So I want to see the output in LED glowing format. So I will go to LED lines. These are LEDs. There are 8 LEDs available on Zed board. So I have to uncomment these lines. Here the comment is this symbol, asterisk symbol, not the double backslash as in the case of Verilog code. Here the comment is asterisk symbol. I am uncommenting 4 LEDs and I am assigning that to my Q0, Q1, Q2 and Q3. So my 4-bit output is 4 LEDs and my input clock I am assigning it to the system clock GCLK. CLK. Uncomment this line. And the other input is reset. I am assigning it to one of the switch S0. Reset. Uncomment this. Now your XDC file is ready. Save it. Now do the implementation step. Run implementation. Yes. Since we have added XDC, it will do both synthesis and implementation. Now it start doing the implementation. It is doing first synthesis, then it will do the implementation. Once the implementation is done, you can connect the board by using open target. Once the board is connected, you can dump the code by using program device. So it will take few moments to generate the implemented design. The synthesis is complete. Now it is initializing the design. You can see the steps that it is following. It will follow the exact same steps that I explained in FPGA design flow. First, it is initializing the design. Then it will do placement and routing steps. You can see here. Running opt design, it is optimizing the design by using best possible logic gates that it is having. After the optimization step, it will do route design. It is routing the design. Routing means connecting different blocks inside your design. After routing, it completed the implementation. You can view the reports or you can go to the next step called generate bitstream. I am generating the bitstream file. I am using maximum jobs. Okay. Since the implementation is done, you can see the implemented schematic as well. And you can even report the implemented power and all. So this is the implemented design. Now it is running the bitstream. Once the bitstream is ready, we will dump that file inside our Zed board. So the bitstream file will save at the same location where the project is created. In this location, I have created the project. So here in the simulation folder, you will see the bitstream file. So it's running. We will do all the steps like setup, hold, and slacks in advanced topics. Now the bitstream file is generated. I am opening the hardware manager. Okay. Now since I have connected my Zed board to the USB port, it is showing program device. Otherwise, you have to do open target and auto connect. Once you connect the target, it will give you options to program the device. So I am programming the device. As I already told, the bitstream file will available at the same location where the ripple carry adder project is created. I have created this project here. So ripple carry adder. In the sources folder, you can see different sources that you have added. Like since you're only seeing bit files, it's not showing, but let's see. This is the Verilog code of your ripple carry adder. And this is the constraint file that you have added. This is the constraint file that you have added. And this is the simulation source that you have added, top underscore RCA. Now the bit file is located at simulation behavioral no, not here, implementation, because this folder consists all the simulation results. So you need to go to dot runs implementation. Here you will see rca.bit. Now select this file and program it on your Zed board. As you can see, the four outputs corresponds to the Q values. Why it is all the four outputs are 1? Because the clock frequency of this Zed board is 100 megahertz, which is very high. So all the four LEDs are going from 0 state to all one state. You cannot even see it. But if I press the reset button, all of them will go to zeros. Since I have assigned reset button to this switch, I am turning on this reset button. So all of them went to 0, right? Now I am turning off it. So all of them are again going for 1. So if you want to see the count, you have to decrease the frequency of your clock frequency. So how to do that? I have written a clock divider code. Right now I will not explain the code, but understand that the clock divider code will divide your clock frequency to whatever frequency you want. So let me copy the clock divider code. So let's put the board aside. If you want, we can write the clock divider code from scratch also. Let's take a register of div clock. So this is my, or I can write a new clock, which is a clock with low frequency, so that I can see the outputs. So I need a counter for it. So I am calling a counter with integer. Now I want to write a clock divider code. How to write the clock divider code? I will use an always block, always at the rate posage of my original clock. What I want to do is always begin if, first of all, I want to initialize this new clock and count values to some values. Initial begin my new clock is equals to 1 tick binary 0. Initially I was assigning the new clock to 0 and my count variable to 0. Now always at the posage of clock, if my count is equals to some very high number, so that this many clock signals are passed, which means if my clock frequency is 100 megahertz, so it is divided by this will give you the frequency of your clock. How many times? 1, 2, 3, 4, 5, 6, 7, 8. So I think it is sufficient. You can see the output. If my count is equals to this value, then begin my new clock is equals to negation of new clock. If you don't understand this, don't worry, we will explain this in the future slides properly. Right now, just consider I am dividing a clock with, I am attaining a low frequency clock using the main clock. So, and count is equals to 0, else my count is equals to count plus 1. And now I have created a new clock. I will call this new clock in my design instead of my system clock. Okay. Now I am saving this and I will do the bit file generation again. Because I modified the code, it will do all the steps from synthesis to implementation one more time. Once the bit file generation is done, you can dump that new bit file to see the output. So don't worry about these syntaxes. What is this always and what is this at the rate, what is this posage? We'll explain these things in Verilog modeling module, Verilog modeling sessions. So right now just consider this as a clock divider code. The code is clock divider. So it is initializing the design. In few seconds it will generate the bit stream also. So once you do the initialize again, it will automatically erase the old design. So the old bit file is now erased. So if you want to compare with old design, you have to copy the old bit file to some other location. Right now the old bit file is already, it was overwritten. See, there is no bit file. It is generating the bit file now. Again, it is doing all the routing steps. Once the bit file is done, we'll dump that into our Zed board. Now it's running the bitstream file. It is done. So program device with the new bit file, program, and done. Since we have given very huge delay, it is not even started. See, it will start after few seconds of delay, 10 seconds of delay. Again, after 10 seconds, it will go to 10. See, I have one more bit file which is at 1 second delay. So I will dump that bit file to show you the exact 1 second delays. So now see how beautifully the outputs are changing from 0, 1, now it is 9, 10, 11, 12, 13, 14, 15. Again it will start from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So this is it for this session. In the coming sessions, we will go and see what is the different types of modeling that are available in Verilog. First, we will start with theory and then we will do lot of examples just like this session. Thank you.